So yeah, so we are going to do two more problems. Perhaps little more involved than the others, right? But before getting there, Sonika asked a question during the break. So we defined this pivot at largest monotone. This problem. So it's really is it really a generalization? Yeah, that's correct. So it's not really a generalization. As you can see, it's the same problem, right? Because given a sequence, this number p, we can as well go and kill initially itself all the numbers that are lesser than p and go back to the original one, right? That's all it's saying. So it's not really a generalization. It's more of a tweaking, rephrasing that that helps us in writing out these recurrence relations in a clean manner. So yeah, it's not really a generalization. More of tweaking or rephrasing. Okay. So we are going to do two more problems now. The first one is the Bellman-Ford algorithm for the single source shortest path problem. So some of you might have seen this also already, but I hope there is something new to learn from this discussion. So this is this is a single source shortest path problem. So this is the problem. So you are given a graph, right, an undirected graph with weights on its edges, right, and there is a specific vertex given to you called the root vertex, like this. What you want to do is find the shortest path to all the other vertices, right? Okay, so the shortest path in terms of the sum of weights on that path. So for example, this shortest path, this is the solution. There is this shortest path to A, from A to C. It goes to B, then goes to C. So its distance is 5. 1 plus 4, 5. So you can see the path to E. It says that I will go like this. That distance is 1 plus 2 plus 5, right? So that's what we need. Find the shortest path or the shortest distance, let's say, to every other vertex from starting with this root. So now for this problem, we know that there are different algorithms possible. One is the Dijkstra's algorithm. So we are going to see another algorithm called this. It's a classical algorithm called Bellman-Ford algorithm. So you can see the pictures of Bellman and Ford here. So Bellman is one of the pioneers of dynamic programming. So he was one of the earliest to use this paradigm. He's the one who coined this term dynamic program also. Right? The Ford, I looked up who this Ford is on the net, on the wiki, and it's same as the Ford Fulkerson algorithm, right? The same Ford of max flows and so on. Right? So okay, so let's keep going. So how are you going to design an algorithm for this problem? So the thing is that we are going to construct instances, sub-instances, and again the same thing, but these are going to be more involved, So in the previous case, it was like simply like a suffix or a prefix and so on, segment, this and that. Now it's going to be slightly different. So let's see that. So now we have to first distinguish between distance and hops, okay, before we do this. So distance is the sum of weights on the path, right? Like, so I have this path here from the root to this vertex called U. Its distance is 40 on this edge plus 30, say 100. There is another path here who is also of distance 50 plus 50, but he has lesser number of hops. He has 2 hops, root to Z, Z to U, 2 hops. Whereas this guy has X, Y, U, he has 3 hops, right? Now, there may be multiple shortest paths possible from the root to U. Now, among these, right, if you look at these different shortest paths, each one will have its own hop count, right? So for example, let's say that 100 is the shortest distance possible from root to U. We have shown 2 paths here, right? Both of them are of distance 100, fine, but one has 3 hops, another has 2 hops. So let's call this as the hop count, this 2 as the hop count. What is the minimum number of hops that you can do and the shortest distance? Among all the paths that have the shortest distance, what is the minimum number of hops, right? So in this case, 2. So let's call this the min hop of U or the hop count, something like that, right? Okay. Now, what to do is actually find shortest paths from root to u having the minimum hop count. Okay, so that's what eventually this essentially this algorithm goes after. Okay, so and it's based on this simple but very important observation, right? So the observation is this: suppose I start from the root, and this is the path, right? The shortest path from root to u. Let's say, right? This is the path. Let's say it uses k hops and its distance is 100. Now, we'll ask the question, who is the guy who appears just before you in this path? Okay? As you are coming down, whom did you see just before touching you? Let's say he is V. And what is his edge weight? Let's say 10, right? Then then the distance from root to V, right? This distance from root to V is 90, right? So now, it's simple that this path you are seeing here, right? That is actually shortest path from root to V, 1. And secondly, the number of hops in it is k minus 1. This guy has k hops. This guy has k minus 1 hops. The distance here is 90 because 90 plus 10 is this 100. Now, this is the shortest path from root to V, and it is the least hop path from root to V. Right? So that's the observation. Because the reason is very simple. If there were a shorter path from root to V, let's say there is a path of length 80 or something, right? Then why am I coming via this path? I could take that 80 path, come V, reach V, then take this same 10 and go to U. I'll get a path of length 90, right? Smaller than this 100. So therefore, I cannot have anything smaller than 90 possible from root to V. Similarly, I should not be able to reach from root to V in distance 90 using less than k minus 1 hops. If I can do that, then I can do the same thing and get something less than k for u, right? So that is the thing. So what this means is that if I want to find the minimum hop shortest path to u, it suffices. I can actually build it from the minimum hop shortest paths to my neighbors, right? I go to my neighbors, look at their min hop paths, and from them I can extend a bit and I can get the the minimum hop shortest path to u. It has to come via one of my neighbors, right? And now the other observation we made is it should be a path of length k minus 1, right? That min hop path. So if I know, if I have already done with k minus 1 hop paths, right? If I know that kind of information, then I can just look up neighbors and extend by one step, and I can get my min hop path to u, right? So that's the idea. So this tells that look at your neighbors, extend it. Another thing it tells you is that go after these min hops, right? Because first do the k minus 1 hops, then you can get the k hop people by going one step further. So that's the observation intuitively. So therefore, if you look at the shortest path structure via these min hop paths, it will look something like this. All the people for whom the min hop is k equal to 1, they will sit right next to the root. They can just go from root to them in one go, right? One hop. Then there will be all these people sitting in the next layer. They'll be at k equal to 2, right? They go 2 stops. Then there will be people who need 3 hops to get their shortest path. Then the people with 4 hops. Then the people with 5 hops. Now, our observation suggests that these 2 hop paths, right? They can't directly come from root or something, right? You can't directly make that jump. It's 2 hops. You first come to one of these people in k equal to 1, then come here. Similarly, if you want to come to 3, you better come from 2, right? It should come from 2. Similarly, k equal to 5, it can only come from k equal to 4 people. There can be multiple choices though, right? Maybe for this guy, for example, I can come via this, or I can come via this, fine. But it has to come via that layer. In this case, these 2 people are my neighbors, right? So, if I constructed this layer somehow, these paths, then to come to these paths, the paths to these people, I can simply go to the k equal to 1 hop paths and look for my neighbors, extend it by one step, and I'll get, shortest path at this layer, and keep going like this. That is the idea, right? So, given that intuition, so our recursive instance that we are going to construct, what it is going to do is, it's not really going to split the graph or something, but it is going to go after this number k. How many hops, sir? That's what we are going to look at. Okay. So with all this, discussion, let's generalize this a bit. That will make the recurrence relations very clean. With all these ideas, we're going to generalize our problem a bit, or maybe call it as a tweaking, right? Now, what we are going to do is that since we don't know the min hop counts actually, right? For any vertex, we really don't know what is the min hop count, right? We really don't know where it is sitting in here, right? So we are going to compensate it by trying out all possibilities for this min hop, and this generalization is going to help us do that, right? So this is the generalization. We are going to say that distance of uk, I'm going to define this quantity. It is the shortest distance from root to u using at most k hops. Okay? It is similar to the shortest path problem. I want to find the shortest path to u, but here what I am saying is I allow you only k hops. Now what can you do? Right? Now if I allow you any number of hops, then you will get the actual shortest path. These shortest paths will somewhat be longer than that, right? Because I am restricting you. Maybe that from maybe from some vertex to you, root to u, maybe the actual shortest path is 100, right? 100 long, right? It has 100 hops. I may ask for only 50 hops. Then you may not really be able to do that distance, right? The real shortest distance, but do as much you can, right? Do as best as you can. Do only k hops, but do as best as you can. That is this problem. Okay? So this is slightly, this is the parameters. Undirected graph, weights, root as before, but you get this extra parameter. How many hops do I allow you? I allow you only k hops. Now find the shortest path from root to all the other vertices using at most k hops. Now it's possible that there is no path from the root to u using k hops. Maybe all paths, shortest or not, any path, it needs more than k hops, in which case think of it as infinite distance, right? I can't even reach him in k hops. Fine. Now, let's see this picture. Is this problem definition clear? So that is the slight generalization or tweaking. So k equal to 1, that problem is easy. It's just this first layer, right? K equal to 1 is this first layer. All you have to look for is, am I a neighbor of root or not? If I am not a neighbor of root, I don't even have any chance, right? I can't do it with one hop, so it's infinity. Whereas if it is k equal to 1, there is only one way, just go from root to him, right? So that is the base case. K equal to 1 is easy. Just this first thing, one straight hop. Other things, we are going to slowly build it now, right? Like we are going to go from k equal to 2, k equal to 3, we'll build layer by layer. That is a dynamic programmer recursion. We are going to go layer by layer. Okay? So let's see that. Let's see the recurrence relation. So we are asking for what is the shortest k hop path to u, right? That's the question. What is the distance of uk? What is the distance to u using only k hops? That is what we want to answer. We know that such a path should come through one of the neighbors, v1, v2 or v3. Let's say I have 3 neighbors, v1, v2, v3. It has to come through one of them. We also know that such a path, this should be a path of length k minus 1, because this whole path is k. So this is the path of length k minus 1, and it should be the shortest distance then, right, to v1 using k minus 1 hops, right? Okay. So meeting okay, so these are all the information we have. So it should come through one of my neighbors, and to the neighbor it's only k minus 1, and up to the k v1 or v2 or v3, whatever path it is, it has to be the shortest path to them. That much is sure, right? So the only thing I don't know is how does this path, through which vertex is it coming to you, right? Does it come through v1, or is it this v2 guy, or is it the v3 guy? Which one is the one, right? That's the only information I don't know. So what I can do is, I can try all those guys. There are only n of them, right? How many neighbors can I have? Not many. So we are going to minimize over all the neighbors v, right? Try every possible neighbors v. if I am choosing this V1, what is it that I can get? I have to pay this distance V1 K, distance of V1 comma K1, that I need to pay. I need to pay also this VU V1, right? This weight also I need to pay. This plus this. In this case, this is this plus this or this plus this. I need to pay that. Whoever is the minimum among these three, that is the best for me to, right? So the distance of U comma K is minimum over neighbors of V, distance Vk minus 1 plus W of V. This is what I will get if I choose V as the option. And now I minimize it over all possible neighbors. So that is the distance of from distance to U using only K hops. Right? So that's the idea. Now there is a small bug here, which is we want, our problem definition says at most K hops. Okay. Now therefore I don't need to go via K hops, right? Why do I force V? Maybe I can, maybe there is a shorter hop possible to me, maybe K minus 1 itself, there is a better chance to me, right? Maybe K minus 1 hop path is better to me, right? So we are going to add that as well. This is if you really use the K hops, that's what we wrote here. Now if you really want to use only K minus 1 hops, that we already solved, right? This we know, right? This is like recursively going back, right? So we have already done K minus 1, so you can go and look for it here. So either do the K minus 1 itself, or if you're doing exactly K, then do this, right? And the minimum of these two options, that is the utmost K path to U. That's the recurrence relation. Any questions? Yeah. True. So in some sense, this thing is included in one of these actually. Yeah. Okay. I thought that I did explicit. Okay. Yeah. Fine. That is correct. So this one is, how can you reach U via some other way? True. It's through one of these and it's actually included here. Yeah. We can remove this actually. Yeah, just this. Yeah. Yes. When you say dist V K minus 1, right, that will include K minus 2 also. Yeah. That is true. We don't need this first term, I was wrong. Yeah. Because, in some sense, this will be included in this itself, right? Like, when you say Vk minus 1, it includes Vk minus 2 in some sense, right? It includes at most K minus 1, so it's already there. Yeah. Yeah. Maybe we need to be careful in the very beginning though, if you want to remove this thing here. So, for example, K equal to 2, then this would say that you are forcing it through a neighbor. Maybe there is a direct link from root to U, right? An edge. So maybe that is the only case. Maybe I don't go through any, maybe I don't go through any U. That may be the only case, right? Like maybe there is a direct hop from root to U, in which case there is nothing called a minimization over the neighbors. Maybe, in that case root is my neighbor. Fine, and put root equal to 0. Sorry. Yeah, we really don't need this. Root itself is a neighbor in that case. Okay. Cool. Yeah, so that's the recurrence relation. This is a redundant term. There's nothing wrong in having it there, but it's kind of redundant. Okay, so that is the thing. Now let's write down our algorithm then. Right? So we are a little more mature in the second session. So we are not really going to do these things anymore for the rest of the talk, like drawing these trees or drawing these things, etc. Right? We are not going to draw these trees, etc. Okay. We are just going to write the recurrence relation and perhaps the final program. So that's what we are going to write now. This is the algorithm then, right? So the first line is you have to guess through the minimum hops, or rather you have to go layer by layer, right? So that is this first line, K equal to 1 to n. Layer 1, layer 2, how many hops, right? That one. Then we have to see whether that U appears in that layer. So we are going to go like this, here, that is the K loop, and then we have to give a chance to every U to kind of get into that layer. So that is this. We go through every vertex u. So we are going to compute this distance uk, right? Now, maybe this is also not needed. You can put infinity or something here. But let's say, I initialize it with k minus 1. Okay. So because I wrote it that way to match up this, right? To match up this term. So up to u k minus 1, I know some part, I already know some distance. Up to k, that distance is itself good enough. That's one possibility. So that is my current best distance, right? uk minus 1. Now, then I think about, can I get, by extending neighbors, can I get a better thing? So I go through every neighbor. That is this loop, right? I go through every neighbor and write the recurrence relation. Now, this is the weight I will get if I use this neighbor, right? Vk minus 1 plus wuv. This is the distance kind of proposed by this v. He can guarantee me this. But now I need to take the minimum over all these people. So if this d is smaller than what I already have, I accept it. Accept the proposal. Otherwise, I reject him, saying that no, I don't want you. So that is the layers. This is for every u to compute duk. And this is if it is smaller or not. No, minimize over the neighbors. That's the algorithm. Now, what is the running time? Okay, we can actually think through sub problems, all these things, but we can also start at this program and say, okay, there is a k loop here, which is size n at most. That is a k. There is a for u loop here that can take at most n vertices. Neighbors is here, another loop that can take at most n vertices, well n cube. Now this is the minor adjustment at the end. So that is a n cube, 3 loops, each of size n. Now you actually wanted just the shortest distance, right? You really don't, in the original problem, we really didn't bother about this k or anything, right? Just find me the shortest distance. I really don't care about hops and all, right? So what I can do is, I can read it off from these tables, right? Distance un, which means that what is the shortest distance allowing at most n hops? That is the maximum possible number of hops. So the minimum distance from root to u, if we don't care about how many hops, is simply read this entry, distance of un. That is the minimum distance. So therefore, our algorithm now finds the shortest path. Its running time is at most order n cube. Any questions? Now, you might have also seen Dijkstra's algorithm. This is a remark aside. You might have also seen Dijkstra's algorithm. So, this algorithm, right, this Bellman-Ford algorithm is one of the earliest constructed dynamic programs. If we really compare this with Dijkstra, let me just make a remark. The thing is that what exactly is its running time? Let's think through it. It's more like this actually. You can tweak it a little bit to ensure that, you have to tweak this a little bit, this algorithm, so that you don't actually run through all the m, but you run through only as much as needed, right? If there is an oracle, like a wise man, who tells that none of these shortest paths, the minimum hop paths, take more than 10 hops, man, I really don't need to run through all these n, right? I'll just do it up to 10, right? So, and that can actually be done. You can set it up in a slightly different way so that the algorithm doesn't run up to k. It runs only up to k steps. That minimum steps, right? In other words, that will be same as this number of layers here, right? So in this example, in this picture, there are only 5 layers. Everybody just sits in 5 layers, even though theoretically, potentially in the worst case, they may go up to n layers. But in this example, they are sitting up to 5 layers. So this algorithm can be tweaked to run in just 5 of the outer loops. Now, such a thing is very useful actually in parallel programming, right? So you can't actually parallelize Dijkstra's algorithm because he actually will go for much longer number of iterations, these outer iterations. Whereas Bellman-Ford is much better in parallel sense because this outer iteration is much faster. It converges faster, and the inner iterations, these things, right? These things can be parallelized in the sense that for each u, all these u can act independently, right? If each u has got its own, it can work independently on its own, then I can find my shortest, I can check for this neighbors myself, while somebody else does, his own stuff, right? They can run in parallel. So then the only thing that will determine the overall parallelism is this outer loop where they have to come and merge. Right? We do this inner loop once, we come and merge, and then we keep doing this for times. So in that sense, minimizing that k is a nice thing. So in that sense, Bellman-Ford is a good algorithm for parallel programming. Okay, so that's an aside remark. In the worst case, this is n cube. That's the worst case running time of this algorithm. So now our last problem that we are going to see in this discussion, which is the bin packing problem. Again, I don't know too much about the audience, so some of you might have seen this, some of you may not. So let's see. But I hope there is something interesting to see here. Now, the bin packing problem differs from the other problems in the sense that it's an NP-hard problem. All the problems we have seen so far are all solvable in P. Okay? With a caveat that the subset from problem is, okay, there is some pseudo polynomial, etc. But for our discussion, let's say they are all run in polynomial time, whereas this bin packing problem is it's an actual NP-hard problem. So we can't find the optimum just the way we did in the other cases. So we are going to design some faster algorithm, an exponential time faster algorithm. So I wanted to give a example of that form where dynamic program helps you to even speed up things that don't have a polynomial time algorithm, right? NP-hard, your exponential time, but you better be, better exponential, smaller exponential time. So an example of that is the bin packing. So let's see this. Bin packing problem is the following problem. You have a set of items, okay, like this. Each item has a size, or you can also think of it as a weight. Okay? So this guy has size 2 or 2 kgs, 3 kgs, 5 kgs, 6, 7, 10 kgs, 12 kgs. So now what you want to do is, we want to pack all these things in containers to be sent out. Okay? Containers or bins to be sent out. Now these bins cannot hold too much weight. Okay? Each bin can hold only this much weight. If you put more weight, it will break off. So now what we want to do is that pack these items into these bins and minimize the number of bins. Right? So think of a transportation company that has all these items to send to some other place. It wants to pack it in these containers and send, but each container cannot hold more than certain weight. We want to pack it in minimum number of containers. That's the idea. So here is a small example. Suppose these are those weights or sizes, and now suppose my B is the size of my bin, right? For our purposes, all bins have the same size, have same weight they can hold or capacity. Here, a lot of space here. Unfortunately, it can't put this 5 anywhere, right? It can't put it here because that will become 17. It can't really put it here because it's already 13, so it will exceed the 15 budget. So yeah, there's something wrong with the solution. 4 bins, wasting space. Now, this is another way, right? You have to rearrange it, and you can actually make it do into 3 bins, right? So you put the 10 and 5 here, 12 and 3 here, 7, 6, 2. That is another 15. So this is nicely packed, okay? So not all input instances, the optimal solution will be this perfectly packed. We are not looking for perfect packing or anything. Just minimize the bins, leave out space, that's also fine. Minimize the bins, right? Okay. That's the idea. Is the problem clear? Now, have you seen this problem before? Something of this form? What is this problem? Now, what if I allow only 2 bins and I ask you, can you do this, right? And set the B to be the sum of these numbers by 2, right? So what if I sum up all these things, divide it by 2, and make that as the bin size, this budget B, and ask you to put it in 2 bins? I ask you the question, can you now do it in 2 bins? What is this problem? Two bins, and the budget I give you is half of the total weight. Okay. So the this lecture. Yeah, one of the problems we have seen is the special case of this. If you make the bins to be 2, if I allow you only 2 bins, and make the sum. Okay, so let's consider a special case of this problem where now this guy says that minimize the number of bins. Instead, I'm going to ask you, can you do it in 2 bins, right? And the budget I give you is half of the total weight. Okay? Take the total weight, make the container capacity as half of that sum, and I ask you, can you do it in 2 bins? Okay, that is the problem, right? A special case or a variant of this. So what is that problem? That is the subset sum problem we saw, right? What is the subset sum asking for? It is saying, can you find a subset of a target, right? I give you a target. Can you split it into 2 parts where one part matches up the target? So it's kind of that, right? Like I give you 2 bins. The sum is half of. If we can perfectly fit it, we'll get that half as the target, right? So this is actually a generalization of that subset sum. Just that there, the subset sum is only focusing on can I do it in 2 bins. That's essentially what he wants to do. Split the set into 2 parts. That's his goal. Bin packing is little, more generic. It says that maybe 2 parts is not possible. Maybe I'll go with minimum number of parts, kind of, right? So now, if you want to do it in 2 parts only, right? We know that we wrote the dynamic program. It was running in polynomial time, like pseudo polynomial, this NT time. Whereas if you actually ask for, allow for this multiple bins, then that such kind of dynamic programs don't work. Okay, the kind of dynamic program that we wrote for that subset sum, so they won't really work here. Okay, and this problem is actually, we can prove that such kind of things don't work here. Right? There is a theoretical term for it, that this is a strongly NP-hard problem. This problem is NP-hard in the strong sense. It will not allow dynamic programs generalizing that subset sum. Okay, so I cannot get that kind of algorithms for this problem. So, okay, well, what can we do? So that is the next thing. Now I can try the name method. Now what you can do is that you can try to all possible ways to partition the set, right? So that is one way. So that's the name method. So this is all the input items. You say, okay, I'm going to try all possible partitioning of this, right? Maybe I'll put 2, 3, 6, 5 here, 7, 8, 10. This is not even feasible because this 2, 3, 6, 5 is adding up to more than 15. I kill it. Okay, another choice, right? I take up this choice. Okay, maybe I'll put 2, 5 here, 6, 3, 7 here, 10, 12 here. That's also not possible. 10 and 12 is crossing the 15 budget. Now, you keep on sit down and write first of all a program for generating all possibilities, right? Ways of partitioning this, and for each one of them go and check whether is every bin okay, is it within the budget bin. Then among those, choose the one that use the least number of bins. That is a name method. Now this name method will use what is the running time is the number of ways to partitioning a set. Given a set, how many different ways are there to partition it? That will be the running time of this program. Now that number is quite huge actually. It's called the Bell number. Okay, number of ways to partition a set. It doesn't have a closed form, but it's almost like an exponential thing. Okay, it will be like this. This will be very badly exponential. I'm not sure whether it's my full screen or what. So it will be looking like this. It's like roughly like n to the m. That will be this number. Okay? Not exactly that, but roughly of that order, n to the m. Okay? So I again took up this chance to look up Wikipedia and why they are called Bell number. So it seems these numbers are known again to Chinese, Japanese, Arabic, this old people, but they were in the modern times they were studied, by E.T. Bill. So they are named after them. So that's where they are. So it's a big number, n to the m, right? Like even 4, 5 to the 5 is a big number. Okay. So now, is this clear so far? Now what we are going to do is, so this is an NP-hard problem. We can't find polynomial time solutions. we have this naive algorithm, and this algorithm runs roughly in something like n to the n. Right? Now, what we are going to do is, we are going to do something more modest. We are going to just still be exponential, not polynomial, but better exponential. We are going to run in time 4 to the n. Yeah, right? So, well, that's what we are going to do. It's still big, but it's not as big as this. So the reason I picked up this was to show, can be applied to dynamic programming, can be applied to NP-hard problems, and also we are going to see some somewhat complicated structure, more complex structure in its recurrence relation, somewhat. So I wanted to show that too as the final thing. Okay, so what are we going to do? So the idea is simple. What we are going to do is, we are going to guess what goes into the first bin, and then we will recurse. That's the idea, right? That's what we'll do, right? So guess that this is, so we want to say this is the sequence. I'm going to make a guess on what goes into this first bin, right? Let's say I made the guess that maybe the first bin is made up of 1, 3, 4, right? Immediately after make that guess, first of all, ensure whether that guess is meaningful, whether it's legal, right? By checking whether do these numbers add up only up to B, right? You should not cross B when you make this choice. That's the only condition. Now, only check that. Once you have made that check, then you are fitting in this bin. Fine. Then what can we do? We can actually go and take the other things and do the recursion on them, right? Solve the remaining part, solve it recursively. So therefore, we can write our recurrence relation like this. What is the minimum number of bins required to do an instance I? It is this. You guess all the possible subsets of I. This is your guess for what goes into the first bin. Check that it's feasible though, right? That it's less than B, that sums up to less than B. It can fit that first bin. Once you have made that choice, okay, there is a bug here, bad bug. This should be S minus I, right? What is the minimum number of bins to do the S minus I, right? Of course, this is I minus S, right? Okay. Yeah. So you guess the I, make sure it's feasible, then go and recursively solve I minus S. This should read I minus S. That's the thing. Once you find the minimum of it, of course, we have to add a 1 to this for our first bin, right? We picked out this S to be put in the first bin. So you have to say that is the 1 bin to use, right? 1 plus that. This will be the best for this bin packing, right? This is the minimum. Okay. So now this guy, this recurrence relation, right? If you look at it, number of sub-instances it generates, it's like all the subsets of I it generates, right? It will be like 2 to the n. So now, yeah, so it's pretty big though. The number of sub-instances generated by each guy. You give an input, it will generate 2 to the n, all subsets, right? Like roughly like 2 to the n many sub-instances it will generate. Now, if you look at the subproblem structure, how will it look like? So we want to get the explicit algorithm here, the memoized algorithm. No, there is really no reason for that. The sorting doesn't help you. So in this case also, it's this diagram. This 1, 2, 3 are not weights actually; they're just element numbers. I just pick the first element, third element, fourth element, and put it into the first bin. So there are very good heuristics for this problem. Okay? There are heuristics that can actually get you within, I don't know the real number, like 1 bin of the optimum. The problem is NP-hard, right? But there are heuristics which probably can get you within 1 plus 1 of the optimum. Okay? Those guys do sorting and do, but in the case of, we are now after finding the exact optimum, the optimum. So in this case, I don't know whether there are algorithms that can do better by making use of sorting. Yeah. So this will be the subproblem, right? What is the subproblem for us? The subproblem is a subset any subset of the input, that's a subproblem, right? Like in this case, I could have picked any subset as my first bin, then the remaining is my subproblem, right? So any subset of the input can become my subproblem. So the structure will look like this, right? So the biggest element 1, 2, 3, 4, that is my root, right? All the full set. These are all element numbers, not sizes. So 1, 2, 3, 4, all the elements of the root. And then in the next layer, if you see, there will be three subsets of size 3, and then the subsets of size 2, size 1. That is how this will look like, right? So in some sense, it will do something like this. This guy will make use of, he may make use of anybody in this layer or anything reachable from him, right? Anything below. Right? So this is the standard set lattice structure, right? The subset relation, that is a lattice sitting here. And so if you want an explicit algorithm that doesn't use recursion, we can convert this algorithm into a recursive algorithm by just writing this recursion as a program. Or if you want to write an explicit program without using recursion, a memoized program, you can again solve it backwards. Keep going backwards, you will get it. So which means that we have to start solving subsets in their increasing length, right? That's what this says, right? So that's what we are going to do. So this is the algorithm. We first go through 1 to n, k. This is the set size. So I'm going to solve this problem for all subsets of size 1, all subsets of size 2, 3, and keep going up. That is this k, right? Size of the sets I'm currently considering. Then for each subset x of that particular size, what is my goal now is to find what is the best way to do that x. What is the minimum number of bins to fit only that x, right? And this x is of size k. Only size k comes in this iteration now. Now, right, I want to now implement this recurrence relation, right? Minimum over all the subsets, I'm going to implement it. So again, taking the minimum, so I'm setting this to infinity. Then for each possible subset s of x, I take, again another bug here, so bad. So this is s minus x, of course. No, x minus x, fine. No, fine. So this is the minimum number of bins for solving that x minus x. So this s is my choice for, I'm trying to solve the x. This is my choice for the first bin, that is a s. For that I have paid the 1 bin cost. Now I am left with x minus s. I have already put the s into the first bin and paid its cost. X minus s is what I want to solve and find the minimum number of bins now. Now I have memoized it. This is a set of size smaller than k. I have stored it somewhere in this array, so I can read it off, and if this s gives you better than what I currently have, I accept it. So I'm just taking the minimum over all possible sets here. That is the algorithm. So then the number of possible x is, now how many subsets am I dealing with? 2 to the n, and for each of those x, I may have 2 to the n many subsets for that, right? So therefore, so this loop, these two loops put together, they will run for 2 to the n. So many x are there, and then this loop will run for 2 to the n. So the total running time is 4 to the n. Maybe you can reduce it a little bit, but yeah, because this loop is not really 2 to the n. It's like subsets of x, but the x's are of different sizes. So it, there is something smaller is possible, but it won't take more than 4 to the n for sure. So this is an algorithm that finds the optimal solution, and it runs in time at most 4 to the n, right? So I really didn't look up the net though to know what is the best algorithm possible for finding the exact solution, right? This is finds the optimal solution. It has to be like this though, because it's a NP-hard problem, so it cannot be too much better than this. It has to be at least like 2 to the n. Maybe they reduce it to 1.5 to the n, but it will be like some constant to the power n. We are getting a constant 4, maybe we can do better. Just reduce this constant 4 to something else. This base of the exponent. That may be possible. I didn't look up though. But as I said, there are algorithms that are, polynomial time, fast algorithms, simple algorithms. They can actually come within +1 of the opt for this problem. Any questions on this? Okay. So if there are no questions, that's all I have. So nice time designing dynamic programs. Of course, yes. We have to put a feasibility check here. Yeah. Yeah. True. I guess where we are heading for, we'll write something like this. I guess this is where I haven't really thought about it. I wanted to give an example for an FPR problem. So I wrote it up like this. I guess what you say will be better in the sense that we can actually try for a divide and conquer kind of thing. I divide it into two sets. I into I1 and I2. Solve I1 optimally, solve I2 optimally, right? So I can guess for that partitioning, right? That's one way of doing it. Is that where it will go? Not sure. Yeah, I understand what you say though. You would have seen this as a set itself somewhere. Yeah. So, but if it fits one bin, then you would not have really seen it. One bin, right? These are all small guys. Definitely. Of course. Yeah. It's quite possible the score will come down, will be quite small. Yeah. We can actually look up on the net for a minute. What is the best possible algorithm for exponential time for packing? Optimal bin. Near optimum. Optimal. Okay. There is one here. Okay. New algorithm for optimal bin packing. Let's see what it is. Richard core. Okay. What is this? Okay. We need to look it up. So I'm not finding it. Yeah. If I find heuristics, nobody is claiming what is the running time. Yeah. Sure. Thanks for inviting me. It was wonderful. Yeah. Thank you. I hope it was useful.